Okay, so here we are back to discuss more in Chapter 16 on carboxylic acids and esters. We've done quite a bit of carboxylic acid discussion by now. Hopefully you're comfortable naming these things. Hopefully you've gotten the hang of the key properties and those dimer formations and the boiling point consequence of that, and just the plain old reactions of either the carboxylic acid acting as a weak acid with water or deprotonating with a strong base, and you're ready to go further into Chapter 16. Up until now, the carboxylic acids have had center stage, but as you can see here, we're going to focus now on the esters. So this is sort of a 2-for-1 here. We're going to talk about just the general definition and properties of esters, and then we'll go into the naming of esters as well. All right, so esters are similar to carboxylic acids. They differ from the carboxylic acids by the replacement of that H on the hydroxyl group of the carboxylic acid with an alkyl group. So they're sort of like ethers in that regard. So if we think about a carboxylic acid as a carbonyl compound and an alcohol, we can think about esters as a carbonyl compound and an ether. Esters tend to be pleasant smelling components of many fruits like bananas, oranges, strawberries, and that's a stark contrast to the rather unpleasant odor of most carboxylic acids. So it makes a big difference whether you've got a hydrogen there off that oxygen or whether you've got a carbon group in terms of odor. Now, based on that chemical similarity, it makes sense that esterification is how we can build these esters from carboxylic acid. So esterification specifically is the reaction of a carboxylic acid and an alcohol in the presence of an acid catalyst to produce an ester. So if we look at this specific reaction, we take ethanoic acid or acetic acid and methanol or methyl alcohol. We heat them in the presence of an acid catalyst, and we generate methyl ethanoate or methyl acetate, depending on whether we're doing IUPAC or common naming, as well as water. So notice the double arrows. It is a reversible reaction, but that's the forward direction is the esterification process where a carboxylic acid and an alcohol come together to form an ester plus water. Okay, so now that we've seen it once together, let's see if you can do it on your own. In this learning check, you're asked to write the equation for the reaction of propanoic acid and methanol in the presence of an acid catalyst. So please pause the video here while you complete that task and start us back up when you're ready to check your work. Good luck. All right, so notice I gave you the IUPAC name. So propanoic acid is a 3-carbon carboxylic acid, straight chain, and then methanol is a 1-carbon alcohol. So we put them together so that we can clearly see that water coming out. So we put the carboxylic acid head group facing the hydroxyl group of the alcohol, and we sort of circle out an H2O there in the presence of an acid catalyst, and of course a reversible type fashion, we get the ester product and a water molecule as a co-product. So there we have it. Hopefully it was just that easy for you to generate those products. If that's not the case, or if you forgot the water or something like that, hopefully you've learned from that mistake. And if that's not true, if you're still struggling with writing these reactions, we didn't have a whole lot of practice, honestly, beforehand. So please do practice some more. If it's just not getting better, before you get too frustrated, please reach out to me for some help. Okay, let's look at a common ester, acetyl salicylic acid, our good friend aspirin, which is commonly used to relieve pain and reduce inflammation. It also seems to help with stopping blood clotting and heart attacks. Some people are on baby aspirin essentially for the rest of their lives to keep that blood thinned and prevent heart attacks. Typically it's someone who may have had a heart attack or has indications that they're likely to have heart attacks. They're often given a small dose of aspirin every day to help with that. So lots and lots of utility for this particular molecule. It's an ester of salicylic acid and acetic acid. Honestly, it seems like in the body it gets converted back into the salicylic acid, which seems to be its active form. But it's derived from the bark of a willow tree, a white willow bark, and there we see a willow tree in our image. And Native Americans knew this medicinal properties of this particular compound well before the Europeans landed here. So it's well known that this particular willow bark was helpful for these sorts of ailments. If we look at the structure up above that willow picture, we see that this is both a carboxylic acid, a benzoic acid up top, and an example of an ester down below with that carbon 2 of the benzene ring bonding to that oxygen, which is then bonded to another carbon group. That's our classic ester. So there we have it. And the properties, as we said, are typically due to, in the acidity of the stomach, having the reverse reaction where we add a water and we regenerate salicylic acid and acetic acid. One of the reasons aspirin became so popular is because of giants like Bayer. In 1899, Bayer Chemical in Germany produced that ester of salicylic acid and acetic acid called acetyl salicylic acid, aspirin as we commonly know it, and it was less irritating to the stomach than that salicylic acid that was contained in the white willow bark. So we see that process here. In the presence of an acid catalyst and heat, we can have that reversible reaction where we take the salicylic acid and acetic acid and form the acetyl salicylic acid, the aspirin molecule itself, along with a water molecule. And as we said in the text there, it's less irritating to the stomach, although it does seem to get converted right back into salicylic acid and acetic acid in the stomach. That for whatever reason, that seems more tolerable. It does cause some stomach bleeding, even as the aspirin form, but not as much irritation as the salicylic form. And if you happen to be in the Binghamton area, Norwich aspirin was a big pharmaceutical group there, not too far from Binghamton to the northeast in Norwich. Unfortunately, most of that Norwich history, a lot of the pharmaceutical groups that had been there have largely moved away from the area. Okay, looking at another important ester, methyl salicylate, oil of wintergreen. It has a great smell like many of our esters. Maybe you like it, maybe you don't. I guess I shouldn't say it's a great smell. I think it's a great smell. And because of its ability to reform salicylic acid and in its form as methyl salicylate itself, it's used to treat sore muscles. It's a common component of these muscle rubs that you may have seen in the pharmacy. It has a pungent minty odor, so if you like mint, you're going to like the odor. It's quite strong, but if you love mint, you'll love it like I do. If you don't like mint, well then you probably shouldn't smell oil of wintergreen because it's quite powerful. And it's an ester of salicylic acid and methanol as opposed to salicylic acid and ethanol as we saw for aspirin. So there we have it. In this case, we're taking that salicylic acid, reacting with methyl alcohol and eliminating a water in the presence of the acid catalyst and heat to make the methyl salicylate, the oil of wintergreen. Now, in addition to our simple esters, we can also make polyesters. So polyester would be a polymer chain formed by ester linkages. So terephthalic acid, which is an acid with two carboxyl groups, reacts with ethylene glycol to form ester bonds on both ends of the molecule. So if we look at the terephthalic acid, it's a dicarboxylic acid. It has the benzene ring in the middle to keep it nice and planar, and it can grow in both directions. If you have the dicarboxylic acid in the terephthalic acid and then the dialcohol in the ethylene glycol, you can make really, really long polymer chains using this esterification reaction. Same conditions we've seen before, right? High temperature and acid catalyst, and we see these ester bonds, and this is a section of the polyester dacron. So you quite likely, if you have any really smooth, shiny clothing, it's quite possible that you have a polyester there. That tends to be the characteristic of polyesters, and they're relatively inexpensive. They're synthetics. They don't breathe as well as cotton, but they do keep their nice, shiny, soft appearance a little better, in my opinion, than cotton would. We mentioned previously in this lecture that esters give flowers and fruits those pleasant flavors and fragrances. Here's some specific esters from fruits and flavorings in table 16.3. Propyl ethanoate or propyl acetate, depending on which naming scheme you prefer. Again, I'm a proponent of IUPAC, so that's why we have the common name in parentheses, and that's the flavor and odor of pears. If we look at pentyl ethanoate instead of propyl ethanoate, so we've added 2 carbons to the what was formerly the alcohol, we now have, instead of pears, we have bananas. If we go up even further yet to octyl ethanoate or octyl acetate, we have the odor or flavor of oranges. If we cut it back down, and this time we have a longer carboxylic acid and a small alcohol, we have ethyl butanoate or ethyl butyrate. That's pineapple odor and flavor. And then finally, the last one on our slide here, we have a 4-carbon carboxylic acid and a 5-carbon alcohol. We get pentyl butanoate or pentyl butyrate, and that is the flavor and odor of apricots. So again, adjusting those carbon chain lengths on either the carboxylic acid or the alcohol that go together to make the ester gives a remarkably different, although typically pleasant, flavor or odor to the compound. So up through now, you've seen a lot of different names here for these esters. Let's just review how we would name a general ester. I've provided you with the names. Let's see how you would go ahead and determine the names based on structures. So in our guide, the first step is to write the name of the carbon chain from the alcohol as an alkyl group. And then second, change it the ic acid of the acid name to an 8, technically an O8. So here we'll move on and see how that works with an example. Okay, so naming esters, the name of that ester contains the name of the alkyl group from the alcohol and the carbon chain from the acid with the ATE ending. These acids typically have an OIC ending, so they become an OATE ending. So if we look here, we have the carboxylic acid that would have gone to form this particular ester was ethanoic acid or acetic acid. The alcohol would have been methanol or methyl alcohol, and therefore the methyl ethanoate or methyl acetate would be the ester name. Now, how do I know which one has the root from the carboxylic acid and which one's from the alcohol? Well, the one that has the carbonyl carbon was from the carboxylic acid. So that's how we know how many carbons were in the carboxylic acid. Anything to the left of the carbonyl or to the right of it, if we have it on the other side, we can always flip these, of course. They're molecules. They are 3-dimensional. They can flip end for end. But you want to contain that carbonyl and anything to the non-oxygen end of it as coming from the original carboxylic acid, then the oxygen off of the carbonyl and anything to the non-carbonyl side of that oxygen would be from the alcohol. Okay, so we're more than halfway through the course, right? So it's your turn to learn these things by doing. We did a brief example there. Let's see how you do on your own in this learning check. Your task here is to give the IUPAC and common name of the following ester responsible for the flavor and odor of pears. So please don't just look back to that table that had it. Please go ahead and do your best to try to name it using the naming guide we've just tried on our previous example. Stop the video here while you name, start it back up when you're ready to check your work. Good luck. Okay, so hopefully you followed the steps. So step 1 would be to write the name of the carbon chain from the alcohol as an alkyl group. So this would be a propyl from the 1-propanol, the alcohol that reacted. Moving on to step 2, we would change the ic acid of the acid name to 8. So if we look at the carbonyl group. There's the carbonyl and the one other carbon atom attached to it. So this was an ethanoate or an acetate, depending on if you're using the IUPAC or the common. You were asked for both. So it would be a propyl ethanoate by IUPAC naming conventions, or a propyl acetate common name for this particular ester. So hopefully that went well for you. If not, or even if it did, we're moving on to another learning check, so just hold tight. Okay, this time around you're asked to name two esters, so you have A and B. So why don't you go ahead and pause the video here, work out those names, and then we'll go ahead and see how you did when you start us back up. Good luck. All right, so there we have it for A. Looking at the alkyl portion, what came after the O to indicate it was from the alcohol, we have just a single CH3 group in the top case and a CH2, CH3 group in the lower case. So for A, the alkyl group would be named as methyl by IUPAC nomenclature, formal by common naming, and then ethyl by IUPAC for B, or acetyl by common naming for B. But we're sticking with IUPAC, and that's why we just have the methyl and ethyl options up on the screen. Okay, if we look at part 2, we're looking for A. It's 4 carbons, including that carbonyl carbon, so we have to change that ic ending to the 8. So butanoic acid or butyric acid becomes butanoate or butyrate. So we have a methyl butanoate by IUPAC, or a methyl butyrate by common naming schemes. For B, that's a 3-carbon carboxylic acid that went into forming this ester. So that would be propanoic acid, or propionic acid becomes propanoate or propionate. So we have ethyl propanoate by IUPAC nomenclature, or ethyl propionate by common naming. So there we have it. Hopefully those two were relatively straightforward and simple, at least to get the IUPAC name. And if that's not the case, guess what? We've got another learning check to end this lecture. Okay, here we have it, our final learning check for this lecture. You're asked now to draw the condensed structural formula of the following esters. So A, ethyl pentanoate, and B, propyl butyrate. We did a common naming there for B and an IUPAC naming for A, just because you're likely to see both. So pause the video here, go ahead and draw the condensed structural formula, or if you're comfortable with it, better yet, the skeletal structure for these two compounds. Stop the video now, start us back up when you're ready to check your work. Good luck. Okay, there you have it. For A, it's an ethyl pentanoate, so we have a 2-carbon ethyl group after the oxygen of the ester, and we have a 5-carbon carboxylic acid portion that form the pentanoate. So from the carbonyl, we have that counting as carbon 1, and then 4 additional carbons on the other side. For propyl butyrate, we have, again, a propyl group. So we have 3 carbons after the oxygen there that was formerly of the alcohol. And then we have a butyrate, so that's 4 carbons including the carbon of the carbonyl to give the condensed structural formula you see before you. So hopefully those were just as easy to go from the name to the structure as going from the structure to the name has become. If I'm way off, if you're struggling like crazy with this stuff and you just don't know what to do, try a couple more on your own, see if you can get it, but if it's just frustrating you, please don't hesitate to reach out to me for some help. Otherwise, if things are going smoothly, then we'll see each other again for the last lecture here in this chapter.